conceptual examples or simple examples before we get to use this to actual applications. Okay? So let's see what the meaning of this is. All right. So I want to explain what the law means for this law. So I'm going to do a few examples. Okay. Example 1. Here is the first example. Here is a surface, and it's closed. Okay. I know I drew just the line. It seems like just a line, but it's a three-dimensional surface, supposed to be a closed surface. Okay. What's the flux through this surface? Huh? So if there is no electric field whatsoever, so 0, right? The flux will be 0. If the electric field is 0, then the flux is simply going to be 0. Okay. Next, I'm going to place a charge here. Here is a plus charge, positive. Let's say it's 1 nano or 3 nanocoulombs. Okay, that's the charge. And someone asks you, says, what's the flux in this case? Not quite. The flux won't be 0 because this is a plus charge. It will produce an electric field, right? Let's use this color. So this is a positive charge, so it will produce an electric field this way, this way, this way, this way, right? So the flux is definitely not 0. There is a net flux up, net electric field up. So it will in fact be positive flux. But how are we going to find the flux?
Q over S.
Good. You should. So you can find the flux two ways. You can do this integral, or you can say it's Q over epsilon naught. In this case, it's easiest to think of Q over epsilon naught. And this is, because this one, think about why we can do this. We don't know what the area is, and it's going to be a really difficult area. Because the electric field and the area, they point in different directions, right? Because, for example, think of in here, the area would point like this, right, perpendicular to the surface, and the electric field points that way. So it's not going to be an easy problem, even if you know what the area is. It's just not going to work. Not going to be easy. But we can say the flux is equal to Q enclosed over epsilon naught. Now, look at our surface and think, how much charge is enclosed within the surface? Huh? How much charge do we have within it? 3, right? Yeah, 3 nanocoulombs. Yeah. So 3 nanocoulombs. Nano means 10 to the minus 9. Over epsilon naught, which is 8.85 times 10 to the minus 12. I don't know what this number is. Can someone do it and tell me what you get for flux?
339.
339. Thank you. Newtons meters squared per coulomb. Okay. That's the flux. Yes.
So it's basically saying for any enclosed surface, like anything that's enclosed,
Anything.
any shape,
Yes.
say like turn it on itself or whatever.
It does not matter. Yeah.
Yeah, as long as the charge is. Okay, cool.
As long as there is a,
Yeah.
yeah. So if someone says, yeah, good point. So he says any closed surface, yes, it is. So let's say somebody else chooses the following, let me make a green surface. Here is another surface. Like this. As long as this, surface encloses the same charge, it would be the same flux. Guaranteed by Gauss's law. Yes?
If there's multiple charges within a surface, is it just a net?
I'm going to get to it now. Yeah, good question. Example 3. Example 2. So here is the next example. Let's say I have a positive 7 nanocoulombs, a negative 3 nanocoulombs, and maybe positive 5 nanocoulombs, okay? I got 3 charges. And I'm going to make 3 surfaces. Here's the first surface. This one. What's the flux through that first surface? The green surface, okay? So I'm going to write it with green. What's the flux through this one? So it would be the charge enclosed within this surface. How much charge does it enclose? A net of positive 2, right? A net of positive 2 nanocoulombs. So it's going to be 2 times 10 to the minus 9 because it's nanocoulombs over epsilon naught, right? And we don't have to worry about the numbers. You can always do them. But I want the concept for now. Okay. Next one. Let's do the following surface. This surface here. Orange one. What would the flux now be for this orange surface? It's going to be minus 3 times 10 to the minus 9 over epsilon naught, right? For the orange surface. Good. I think you got the idea, but let's do one more. One more is going to be, let's say the surface is going to enclose all of them. Okay? As long as it's closed, what's the flux now? It's going to be 12, 9?
Yeah.
Epsilon naught. Yeah.
What if it isn't closed?
If it's not closed,
Yeah, you said
then
it.
you would have a net flux, and then Gauss's law would not apply. Yeah. It has to be a closed surface. Yeah.
Is it still in 2D?
Huh?
Is it still in 2D?
Everything's 3D.
3D.
Yeah. Yeah, I know this is a line, but it's supposed to be a three-dimensional object. Has to be a closed surface. Closed surface. So everything I have, it's on the board, so it's 2D, but it's really 3D. It has to be 3D. Otherwise, it's open, right? If I just have a loop,
Oh, yeah.
it would be open. It has to be closed. Finally, here is this next example. Example 3. And then we get to apply Gauss's law. Here's a positive charge. Right? Here is a positive Q plus Q. I don't really care about its magnitude. In what direction is the electric field? Before I said, here is a surface. What's the flux through this surface? Huh? Yeah, how much charge is enclosed? None, so 0. So the flux is 0. It's actually equal to 0. Here's the reason, or here's the conceptual reason. Look at the electric field lines due to this positive charge. Let's draw a few of the 3 lines. Here's one line. It will enter, and then it will exit, right? When it enters, what's the flux considered? Negative. And when it leaves? Positive. So every line that enters also leaves, so it ends up 0. Net flux is 0. Look at this one. Enters and leaves. Enters and leaves. So the net flux is going to just be 0. Okay? And as long as there is no net charge enclosed, Gauss's law says the flux, net flux is going to be 0. Yeah.
I think I know it is just so I know.
Is there one open surface?
Yeah.
Except for 3? Is it literally open?
Between the surface of the
Why you talking about the
field,
Yeah, why do you think I would leave that? What do you think? So let's draw 2 lines next to each other. Right? This line, this line. For these, this is the area available for them to enter, but to exit. Yes, they get weaker as they get farther, but there is more area available.
Okay,
And it just works out like that because it's 1 over r squared. Okay, but mathematically, Gauss's law says if you're not enclosed in any charge, the net flux is zero. That's all. Okay. We're going to go to applications of Gauss's law. We're going to apply Gauss's law to the simplest case that we know the answer for, and then we'll go to more and more complicated cases. What do you think the simplest case is? Beyond zero, besides zero. If there is no charge, then zero field, right? That's the simplest case. But, you know, we want something. Well, we need charges. So, how many charges is the minimum?
One.
Two to get a force. But to get a field, just one. So let's apply it to the simplest 1 point charge. I think you already know the answer. I keep resetting. I said example 1, 2, 3, and now I reset again. You will keep track of the numbering. So this one is example, I forget.
4.
Okay. 4, okay.
Yeah.
Not counting the previous 4. The ones on the whiteboard. Okay. But example 1. I guess example 1 in applying Gauss's law. All right. We're going to do it to a point charge. What's the electric field due to a point charge? If you're a distance r from the point charge. Q over what? KQ? KQ over r squared, yes. Or Q over 4 pi epsilon naught r squared, right? And it's radially outward, r hat direction. We already know the answer. We're going to use Gauss's law to arrive at that result. So here is a charge. Charge Q. Okay? Here is charge Q. And the question is, find the electric field due to charge Q at distance r from charge Q. Okay? So to apply Gauss's law, you need to have some symmetry. If you have a point charge, you have what's called spherical symmetry. Here is the reason. Let's say I'm here. If I'm a distance 1 meter from this charge, right? The electric field is something, right? There will be some electric field. Let's say I'm 1 meter, but on this side. Will the electric field value change, the magnitude? Will it be weaker or stronger? It will just be the same, right? As long as I'm fixed distance away, the same distance in every direction from the charge, the electric field will be the same. Okay? It doesn't matter where I am. So that tells you, as long as you're on the surface of a sphere, right? The surface of a sphere, then the electric field would have the same value. So here is a sphere of radius r. It should be centered. Here's the charge. So again, if I'm here, the electric field will have the same value as when I'm here, or here, or here, or anywhere on the surface of the sphere. And that's why I had this bowling ball. I don't think it's bowling, it's just a ball. Oh, won't see it, the camera. So as long as I'm on the surface of this sphere, the electric field would be of the same value, right? The charge is in the middle. By the way, this sphere, this surface, is called the Gaussian surface. It's not an actual surface, there is just a charge, and this one is a mathematical surface. It's a mathematical surface. The ball is physical, but it's just to demonstrate the point. So, in what direction is the electric field when I'm here? Up. How about when I'm here? There. Here, down. Okay. So let's go back to here. The electric field is up. In what direction is the area? Also radially outward, right? It's always perpendicular and away from the surface. So what do you notice? The electric field and area will point in the same direction anywhere on the surface of the sphere. And that's one of the reasons you would choose a sphere and not something else. I would show you choosing something else what it does in a moment, but for now, let's focus on the sphere. So if I'm here, the electric field points this way. Also, the area will point the same way. The area area points also the same way. Okay? And that happens, they are parallel to each other anyway. Okay? Everywhere and anywhere they're parallel to each other. Yeah.
I thought the electric field had to go through the surface.
Yeah, so the electric field lines they leave, right? So at this point, the electric field is pointing that way, right? Okay. So let's apply Gauss's law. Here is Gauss's law. E dot dA. Again, it has to be a closed surface, otherwise Gauss's law doesn't apply. Q enclosed over epsilon naught, okay? Let's worry about the right side for a moment. What's the charge enclosed? Yeah, just Q. That's the charge that's enclosed, it's Q. So I put Q. Let's look at the left side. So there are a few annoying things in this integral, but they all go away with the right choice of the surface. The first annoying thing, there is a dot product. Nobody wants it. And so we need, let's see why the surface helps get rid of it. The electric field and the area are parallel to each other. So what does this reduce to? E dot dA reduces to what? 1. The angle is 0 degrees, so 1, yeah. So it would be the product of their magnitudes. It would just be EDA, right? It would be EDA. It's, instead of a dot product, you would just have the product times cosine of 0, which is 1. So it's just going to be EDA. So E times dA. That's the first nice thing that happens by choosing it to be a sphere. Here's the next nice thing that happens. Is the electric field, this is the magnitude. Is the electric field magnitude here different from here? No. And from here? No. They're all the same. So that means the electric field has a fixed value as long as the radius is fixed. So we're going to pull it out. So that's another nice thing, right? What's the integral of dA? A. And how much is A for a closed surface of a sphere? It's the area here. It's the area of this. How much is it?
4 r squared.
The volume is 4/3 pi r cubed. Yeah, area must have an r squared, so
4 r squared.
pi r squared, 4 pi r squared? Yeah, it's four times that of a circle, yeah. 4 pi r squared. So it's E times 4 pi r squared. This comes from that somehow. Okay. Q over epsilon naught. Let's solve for E. So E would be, divide both sides by 4 pi r squared. And you get Q 4 pi epsilon naught for r squared. And we already knew this result, right? Okay, we already knew this result. And we know the direction, so I'm going to make it into a vector finally. So we're going to put here. So here is, right, we chose a sphere because it's nice in this problem. It makes the area and the electric field parallel to each other, and it also makes the value of the electric field on the surface of the sphere the same. So here's what happens if you chose something else. Let's say it shows like a box is nicer than a sphere, I think, but not in this case. So here's a box. Right? Let's say someone says, I'm going to choose a box. Here's the problem with the box. If you're here, the electric field points this way, right? In the middle. And the area points this way, so that's nice at that one point. But here are problems. Problems start to arise here. If you're here, the electric field points this way, but the area points this way, right? Of the surface. additionally, so the angle is not the same, and it would be a different angle here also, right? Different angle. It starts at 0 and then grows to something. And the other problematic thing is the electric field magnitude here would be, or the electric field here would be less than here, and here it would be less than here because it's farther apart. So you got varying angles and varying magnitudes. So that's a problem. So you would be able to do the right side of Gauss's law, Q encloses Q over epsilon naught, but you can't do the left side. So that's why we chose the sphere in this case. Okay. And usually, if you have a point object, it's spherical symmetry. If you have a sphere, it would still be spherical symmetry. And then there are other symmetries which we will discuss. Yeah.
Or is the charge is on the surface or inside of the
The charge is here
It's on the surface?
at the center.
At the center.
Yeah. It's a point charge.
And so do for the block. Is it also in the center of the block or
For which? For this?
Yeah.
Yeah, it's at the center here. So I'm saying the block, this box, is a bad idea to use instead of a sphere. That's what I'm trying to say. I'm saying the shape that you use for your surface must match the symmetry of the charge distribution. In this case, it's a point charge, so it would be spherical symmetry. And another thing I want to mention is this an actual sphere? Is it a physical sphere? No, it's a mathematical sphere. It's called a Gaussian surface. This is not an actual box either. It's just some mathematical closed box. Okay? So it's not a physical box. It's not like a conductor or an insulator or something.
What would we do differently if we didn't
Then you will have to carry out integration. It's not going to be very nice. I think in the notes I do go over this, and you arrive at the same result.
are we using like the Stokes theorem?
This is called Gauss's theorem, or the
Is that for
divergence
the
theorem.
integration?
Huh?
Divergence theory?
Yeah, it is. Yeah.
Is it divergence also to some? Divergence.
We will mention it at the end of the semester. We will talk about those theorems later. But for now, we just Gauss's law, and we're not going to worry about vector calculus. So that's for a point charge. The next one that I want to do is an infinite line of charge. Infinite line of charge, and then you're going to tell me what kind of symmetry that is. Can I erase this one because I don't really need it? It's occupying space. So an infinite line, it's another result that we obtain. Infinite line of charge. Infinite line of charge. Here's the line of charge. Right? That's the line of charge. So this is the physical object. This is the actual object because charge is here. Okay. And as usual, I just assume it's positive. If it's negative, the only thing that changes is you put a minus sign in front of your electric field at the end. That's lambda. Remember what lambda was? It's the charge per unit of length. Okay. Our goal is to find the electric field due to this infinite line of charge. We already did this. We did it using Coulomb's law, and we integrated from basically minus infinity to infinity, and we found the result for the electric field. We're going to do it using Gauss's law because there is symmetry. And here's how you can think of it. First of all, choose a point. Choose a point here. And ask, in what direction would the electric field be at that point?
Up.
So away, so that in this case it's up, right? And the reason you can think of it as away is if I choose a little dq here, it will produce an electric field away. If I choose a dq here, it will produce an electric field away from itself, but in this direction. If I choose another dq, but in the opposite direction, it will produce an electric field this way. And you can see the horizontal components cancel, and only the one that's away remains. Okay? So we know the electric field has to be away. It's radially out. So I'm going to erase these, okay? Because we already know the electric field is going to be radially out. Can I erase this? Okay. So I know if I'm here, the electric field is this way. If I'm here, it's this way. If I'm here, it's this way. And what if I go around? It's still that way, right? If I go around and along. So what kind of shape is that? That's a cylinder. So you got a cylindrical symmetry. So that tells me if I'm going to apply Gauss's law, the surface that I will choose should be the Gaussian surface. The surface is called the Gaussian surface. That I'm going to choose will be a cylinder. And the axis of the cylinder will be the line of charge. So that's what I'm going to choose. So the surface that I'm going to draw is not a physical surface, it's a mathematical one. The only physical thing is this, is the charge. There are actual charges here, and then the surface I'm going to draw is just something to help us calculate the electric field. So here it is. The surface is going to be a cylinder, it has to be closed. And my cylinder is going to have length L. Okay? I'm just going to give it length L, and it will have radius R, or a distance R, radius R. In what direction is the area of the cylinder of the left cap, or the left end? In what direction is the area? Okay. The A is to the left. In what direction is the field? Up. The field is up, okay? The electric field is up. And how about here? In what direction is the area? To the right. In what direction is the field? Still up, yeah. What angle do they make with each other? Yeah. 90. How about here? In what direction is the area? Yeah, up. It's a cylinder. Remember, it's radially outward. It's this. This is the cylinder, right? And the area points perpendicular and away on the round side, the middle side. So dA points this way, and the electric field also points that way, in the middle part. Okay? So we're going to write Gauss's law, and then we will see what we can do with it. It says, Gauss's law says E dot dA, closed surface, is equal to the charge enclosed by that surface over epsilon naught. Now, a closed integral means I need to include the whole cylinder. What does a cylinder consist of? It consists of a left end, a right end, and the round part, or the middle part, right? That's the whole cylinder. It consists of these three parts. So I can break my integral into three parts. This closed integral is going to be the integral over the left part, E dot dA, plus the integral over the right part, E dot dA, and then plus the integral E dot dA in the middle equals to Q enclosed over epsilon naught. It seems like we made it worse. We took three integrals, traded it for one integral, we traded it for three, but we didn't. Most of them they're going to cancel. They're going to be zero. Okay. The left is going to be zero. Why? They're dot product, right? E and dA, they're perpendicular to one another, so this is going to be zero. And here, the right, also zero. And then the middle, we will worry about it in a second. Okay. Now, how much charge do I have enclosed? my cylinder encloses this portion of the wire, of the chart, of the line. From here to here, it encloses a length L. So how much charge do I find in a length L of this, of the charge density is lambda?
L times lambda?
L times lambda, lambda times L, yes. Charge density times the length. This is charge over length times length gives you charge. Okay, so the right side is done. We worry still about this middle part. Now let's look at the middle. E dot dA. The first thing we always want to do is get rid of the dot product. Can we get rid of the dot product here? Look at E and A, they point in the same direction. So E dot dA reduces to what? EDA. Yes, it reduces to EDA. So I get in the middle, I have EDA. On the right side, I have lambda times L over epsilon naught. Next, is E constant? Yes, because in the middle part, whether I'm here or anywhere here, as long as the distance is fixed, if it's R, and by the way, it goes around, as long as I'm a distance R away from the wire, the electric field is constant. So what do I do to the field? If it's constant.
Take it out.
Yes. So you just have E, the integral from the middle, dA. Lambda L over epsilon naught. Now, the integral of dA is A. It would be the area of the middle part. What's the area of the middle part? 2 pi R L, yeah. So it's L this way, right? It's L this way. Yeah, L this way. And if I unwind it, it would be 2 pi R, right? This way. Okay. So it's going to be, yeah, the surface area of that part is going to be E, and then 2 pi R L equals to lambda times L over epsilon naught. And L goes away, because L has nothing to do with the product. It always cancels. Only R, because the electric field should just depend on R, how far away you are from the wire. So you get, divide both sides by 2 pi R, E, lambda over 2 pi epsilon naught, and then 1 over R, right? And since it's a vector, we can put our vector sign. We already know the direction is away. So we can put vector, and then what, how do I say away? J hat. J hat will just say upward. R hat. R hat. Radially outward. So that's the electric field for an infinite line. You remember this equation? Yes. We got this last weekend.
So then you're using this cylinder because it's easy to integrate, but Gauss law says that any surface.
Any
will
surface,
work.
yeah, yeah.
So it's just saying, like, just using an easy example to prove that.
Yeah, so Gauss's law is always true. It's, the question is it useful or not? So if you don't have the right symmetry or the right shape, then it's not useful. So if, for example, like the point charge, if you choose a box, Gauss's law is not useful.
Oh.
Yeah, so you want symmetry in there.
Well, but useful enough.
Huh?
Like, it's not useful because the math will be worse. but
Yes.
It will still work.
It would still work. Yeah, yeah.
Okay, great.
Yes.
Are there gonna be situations with Gauss's law where you have to integrate?
Usually we, sometimes you might have to integrate the right side to find the total charge. Yeah. Other than that, we always want to choose a Gaussian surface where we just never do an integral. Yeah.
So Gauss's law is a way of proving that formula?
Gauss's law is a way of calculating electric fields by taking advantage of symmetry. instead of just going and doing integrals like by dividing it into many dq's and then directly using Coulomb's law. And so it's a way of taking advantage of symmetry to easily calculate the electric field. Yeah.
So we're given like a point charge or a line charge or a sheet, and we get to choose what surface we use?
Yes, yeah, you have to decide what surface, but usually it's very clear. So sometimes you'll have an infinitely long, in this case wire, sometimes you have an infinitely long cylinder. And what shape would you use? Cylinder, cylinder, yeah, yeah.
What shape would you use for each?
Yeah, that would be the next one. It would be it's called planar symmetry. And we want to use a surface, let's say this is the sheet. I want to choose a surface, let's say like this eraser. And imagine the eraser goes through the board, it's not going through. Yeah. And this part will be parallel to the board, but these parts here will be perpendicular to the board. That'll be my next one. I'm going to do that. It's called planar symmetry. There are three types of symmetry that we use with Gauss's law. There is the spherical, cylindrical, and then planar symmetry. Those are the three.
We do use the square eventually.
We do use the square eventually, but we will see it doesn't have to be an actual square. It doesn't have to be an actual square. Yeah, let's do let's do the sheet. I think I have 8 minutes. So infinite sheet. Right? For infinite sheet, it's sigma. We already know the result, right? What's the result for the electric field? Sigma over 2 epsilon. So here is the sheet. This is the sheet, and the sheet is like this, okay? This is the sheet. All right? So first, we need to conclude the direction of the electric field. Let's say it's positively charged sheet. So if I'm here, in what direction is the electric field going to be? To the right. And again, you can argue, if you take one little segment here, it will contribute to an electric field to the right. And you can take one segment here, it will give you an electric field there. And one segment here will give you an electric field in this direction. So only the ones to the right survive. And the sheet, by the way, extends this way. So if you pick two segments here, they will contribute electric fields like this, but only the one to the right survives. So no matter what you do, it will the conclusion is the electric field will be to the right if you're to the right, and here the electric field will be away from the sheet, so to the left. So that's the first conclusion. So I'm going to take this away. So we conclude that let's choose somewhere here, and I know the electric field is going to be this one, right? And if I'm here, it's also going to be this one. And the question is, how much is it going to be? What is it going to be? If the infinite sheet is sigma. And your surface is going to be this. We're going to choose a surface that's similar to this. It would be here. And so my surface is going to have the round part, either round or rectangular, doesn't really matter. You will see why. And then it will have the area. What I need is the area on the sides to be perpendicular. And then in here it's going to be to the right, in here it's going to be to the left. So